Hi everyone, welcome again. We continue our journey through making our data to talk, to speak to us, because we need to extract information, to visualize some important hidden information that is not visualized to our eyes. So we have to use a chemometrics tool. There are plenty of different tools that we can use for analyzing our data. One of the simplest way to make a calibration or to make a prediction of a certain attribute inside the sample using univariate calibration. What is a univariate calibration? Is only to use only one variable, only spectral data at only one wavelength, or even like a spectrophotometer to have absorbance or to have reflectance or to have transmittance at only wavelength. But if you have 100 samples, okay, of transmittance or reflectance, so you should have at every sample you should have value of concentration. So we need to use the spectral information to predict all of these chemical composition or the concentration. So we need to use a classical calibration using the univariate analysis, using a single compound to predict the single compound. This is a very simple linear regression when you make a comparison between x and y, between this variable x is the spectral data and this y is the concentration, where y is the concentration equal x, and x is multiplied by a constant, and both data are summed with a constant is a. A is the intercept and B is the slope of all of these lines. And of course, the difference between this point and the prediction line is the residual or the error. Okay, so the quality of the prediction using this model, it is a square root of the squared error between the prediction and the actual data of my concentration. This happened if we have only one variable, only one wavelength, only one detector, only one spectral data at one wavelength. But what happened if we have different wavelengths? We have different variables. That means we have different wavelengths at different bands, and then all of these factors, all of these variables should be used to predict the concentration. There are a lot of contribution between the variables or the x variables or the spectral data to predict the same composition, the same concentration for the same compound. If you need to express all of these multiple linear regression, multiple means I have a multi of variables to predict one concentration. So in the univariate, I have only one variable and I have only one slope or one coefficient. But with two variables, for example, I should have two coefficients of prediction or regression and one constant as an intercept. Okay, so we should solve for B coefficient. Once we have the spectral data and we have the concentration, you should obtain the regression coefficient. Regression coefficient means the intercept and the constant multiplied by each spectral data. So I need to know A or B naught. I need to know B1, B2, and if you have 5 or 6 variables, you need to know B1 to B5 to B5 and B6 and B10 and so on. So we need to solve for B coefficient. We need to know the beta coefficients used for future samples that is not analyzed yet. So calculations actually is very simple, but could be very complex. It depends on you. So you need to choose your track. If you are good enough in mathematics, you can choose to make a calculation by yourself. For example, if we have two variables used for prediction of this concentration, two variables means spectral data at only two wavelengths, and these two wavelengths should be used for predictions the concentration of a compound. Could be sugar, could be protein, could be water content, whatever. So this is the equations that we need to solve. Y equal A plus B1 x1 plus B2 x2. Then we need to solve to obtain the beta coefficient A, B1, and B2. This is the data. First step, we need to calculate from the spectral data or from the original data, the raw data, we need to make some calculations. So we can take all of this data to Excel file, for example, and make a calculation for x1 square, x2 square, y, xy, x1, x2, x1, y, x2, y, and so on. And then after this, you make a calculation for regression. After making all of this calculation of summation of all of these parameters, you can easily go with these equations to calculate A, B1, and B2. Once we have these parameters, you can make a substitution inside your original equation, this one. This is original equation, then I have this equation. This equation is ready to be used for future samples, for unknown samples. So if you have samples from the same characteristics, from the same population, just introduce your sample inside this multivariate model. And from this multivariate model, you can make a prediction. The question now, what happened if we have more than two variables? The situation could be more complicated because I have only two constants in addition to intercept. But if you have three variables, for example, the equation could be extended to this very long and very tedious equation that is very difficult to calculate using a very simple calculations like this, because the calculation itself is very complex and very time consuming. But fortunately, we can use matrices. We can use matrix and matrices to solve these equations. For example, if we have spectral data with more than two variables, for example, in this situation is 10 variables, and in this 10 variables, okay, we have 20 samples. So 20 samples and 10 variables used for prediction of concentration for a constituents. This concentration could be C or could be Y. And I need to solve this problem. I need to obtain this equation. But in this situation, I don't have only two variables. I have n variables. In this example, I have 10 variables. So how we can use, if we arrange the data in a matrix form, shall we be able to make a calculation using? Yes, of course, because we are solving for concentration. So concentration equal X multiplied by B. This matrix multiplied by this matrix give us this matrix. Because I am solving for the beta coefficient, we can make an inverse or Z-do inverse, okay, based on the shape of your matrix, the spectral data matrix. So this is a general form of the matrix used to convert the concentration or Y variable, because Y equal this matrix multiplied by this matrix. If this matrix is a square matrix, we can use the inverse directly. Beta coefficient equal X minus 1 multiplied by Y. But if this matrix has more variable less than the samples, or less variable less than samples, that means we don't have a square matrix of X. We have a rectangular matrix like this situation, 10 variables and 20 samples. In this situation, you are unable to use the simple transpose. We need to go Z-do inverse to fake the inverse itself to obtain the beta coefficient. Is it possible to make these simple calculations either in MATLAB or Excel? Yes. Let's go to Excel first, okay, to see the same example, okay. And from this example, we can make a calculation, and then we can know how to analyze. This is, for example, this is the X1. This is X1, and this is X2, and this is Y. I need to use these two variables to predict the Y, okay? So we need to go through the data. Okay, and then you can use regression, linear or linear regression, and then choose your y variable and then the x variables. In this situation we have two variables. Then choose the point where we have to put, or the location where we put our data, and then we choose all of these collections if you are interested to visualize all of this information. Then you have this data, and from this data you have the coefficients. Okay, this is the coefficients. You obtain number of samples and the multiple linear coefficients of your data. For example, here, if you are interested about the constant, this is the A. For example, you can call this is A or A node. Okay, and this is should be B1, and this should be B2. This is the coefficients that we have. These coefficients could be easily used for prediction for unknown samples, but fortunately you can use here the predicted values using these coefficients. You can even use the original data. This is the y. This is the my original data, and this is the predicted data or predicted y. Okay, we can use how close they are to each other. If you are interested to know how these data are related to each other, just go and plot all of your data. For example, we can start from first value at 140. Okay, and this also we can start from 140. Okay, then this is the data. This is the actual data or the original data, and this is the predicted data. For example, we can even add trend line, and from this trend line you can put R square, for example, and the equation. So the R square for prediction using this multilinear models is 0.96. This is how strong this model could be used for prediction of the variable y using these two variables. This is very efficient and very useful and very easy and straightforward to carry out these calculations using the Excel file. We can even go to Excel, to MATLAB, take copy from this data, then we go to MATLAB and then write this is the data, okay, equals, then something very easy, because it is very easy also to import your data from Excel file, but we need something very fast to do it. And then we can name, this is your data, this is y, this is the first column, and then x1 is my data for the second column, okay, or rows, okay, second column, okay, and x2 is my data, okay, or rows for the third column, okay. So I have now y, x1 and x2. Don't forget the equations contain two coefficients. The first one coefficient for x1 and the another one is B2 is a coefficient for x2. But you have to consider there is another coefficient for the intercept. That's why you need to prepare your data, and from this data you have to consider you have coefficient for x1, coefficient for x2, and also coefficients for the intercept. Intercept doesn't contain x, doesn't contain information. That's why we need to add a column that already all of these is one's column, one value. We don't have x variables. That's why we can write x variables. We have ones for the size as the size of x1 for example, because x1 and x2 is the same size. Okay, this is the first column, and then second column is x1, second column is x2, and then close. This is my x. So I have first column is ones, second column is x1, third column is x2. Then we can make a prediction. I can say, okay, it is y2. We use this function equal regress. So the function that is already used for making multilinear regression between y as a variable, okay, and x contains a matrix, contains the matrix of the two variables x1 and x2 in addition to the intercept. So we can have the beta coefficients. If you compare these values, okay, of beta coefficients with the value we obtained from Excel file, it is the same. So we can use this one. We can use this beta coefficient. Okay, I can even write it is not B2, it is beta coefficient. Sorry, it's beta coefficient. We can use these values to make a prediction for your data. For example, we can make a y2 should equal x times the coefficient b. Then this is y2 is the predicted value using this model based on this coefficient we have. Very simple and very straightforward to obtain or making multilinear regression either using Excel or using the MATLAB. Next session we are speaking to speak about something very, very important. It's called principal component analysis. Okay, see you in the next presentation.